Hello everyone, welcome to Lecture 16, Models. I'm your instructor, Ms. Laura Lowe. In Module 6, Week 6, we introduced sampling and models. In the previous lecture, we show you the method of sampling and how to do the random sample and also the distribution of large random sample. Continue in Lecture 16, we will talk about models and we see how to assessing the constancy of the data and the models. Before moving to introduce models, we have two things we want to do. The first one, that's quick review for the distributions that from last lecture. So any random quantity has a probability distribution. So all the possible value it can take, the probability it take each value. After repeated draw, so here is the simulation we show you. After we repeat it to calculate the value, all draws, we have an imperial distribution. So the imperial distribution is an observed result. So all the observed value it took, in that proportion of times, the distribution is our empirical distribution. So from our last lecture example, the United Airlines flight information, we can see after many independent draw, after we simulate a large number of simulation, the empirical distribution look more and more like the probability distribution. So in case you forget about that, let's see the demonstration again to show you. So we continue to have our United table created. So after we have United table created, remember we show you, you can get the median from the whole data according to the column of delays. So we got a median. So this median, since we take the whole table columns, so this median actually is the population median. So this one is according to the all data from the United flights. So the median is the middle number after we have all the delays to sort it from the small to large. So then in the middle value, that will be 2.0. So from here, we also can get statistic results according to the sample we choose. For example, here, we still try to get median, but here we just using the size sample 10. Okay, so then we got median for this 10 result. Okay, so we got the 3.5. So this, like we said earlier, each sample depend on, no matter what your size is, they have their own statistic. So then here, one thing is you can do is, the first 10 you see we choose, they got a median is 3.5. If we perform more, we got a 6, or we got 13.5, we got 2.5. Then you can see we just quickly maybe run, maybe 5 times, for 10 times. Then you can see they are pretty big until even they have more than 20. So then you can see they kind of have big range for the size 10. So the same thing, let's do the same statistic result. We just got our sample size is 100. Okay, we see here, we run few times, we see the result. Then we got 0.5. Okay, then we got 3.0, 1.0. 2, yeah, exactly the same as the population size. Okay, so 1. Okay, so you can run a few times. We just want to show you the result, but at least you can see the range for sample size 100 you draw. They kind of between 0.5 to 3. So we can see here they got a little narrow range compared to the sample size 10. Okay, so what does that mean? So here we need to start talking about the statistic. We quickly talk about statistic end of lecture 15. So basically, statistic is the summary of the data. So for me, when I heard about statistic, it made me think about some value. You see, for example, we have average, we have mode, we have maxima, we have minima, or the median we just show you in the demo. So basically, they're just using a summary to represent the data set. Yeah, we can use different number to represent. So here we want to talk about statistical inference. So statistical inference is making conclusion based on data in random samples. Like earlier we said, you have different, in statistics, they have some value to represent the data set. So here, even we just say according to the sample size we choose, the random sample, they have its own statistic. So those statistics, according to those data, can we make some conclusion based on the data? Yeah, so that's we call the statistical inference. We try to, according to the data, we make conclusion. For example, we use statistics to guess the value of an unknown number. So use the data to guess the value of an unknown number. So this unknown number is what? Actually, it's kind of one data represent for the population. So this unknown number, of course, they have one value. For example, I want to know all the DVC students, what is the average sleeping hours for all the DVC students? No matter what, they definitely have an average number for all the students, right? Just we don't know that. And also it's difficult for us to know. I couldn't get all our DVC students together to answer the question because I need to get a survey. So I'm not sure how many students were involved and something like that. But anyway, we do know there's an average value. So since we couldn't get that real value from our population, so we will create an estimation for the unknown quantity. So this unknown quantity actually is, like we say, depends on the random sample data. We can get the average from the random sample. So that's an estimation for the unknown quantity. So to be more specific to say that, actually I should introduce you about the terminology. The first one is parameter, a number associated with the population. So here the population is like earlier we said, the all DVC students. And the number associated with DVC students, like earlier I said, the average sleep hours. So the average sleep hour is a parameter we are looking for, associated with DVC, all the DVC students. So since I cannot get that, so I will use the statistic to calculate, statistic to represent. That will be a number calculate from the random sample on the sample I create. So a statistic can be used as an estimate of that parameter. So that's why the sample, you see here, I need to get a sample to find the statistic. So that sample can be, depends on how you will do. So of course, in this class, we will show you, we should do a fair and random sample. But how to decide the sample size? Okay, so now earlier I show you, you see the sample size can be 10, can be 100. Every time I run, I have different data. So those data we call is probability distribution. So the value of a statistic vary because the random sample vary. Every time I run this code, they got size is 10 sample. Every time I run this code, its size 100. Every time they find different sample. So that's why your value of the statistic varied because random sample vary. So sampling distribution or probability distribution of statistic, all possible value of that statistic and all the corresponding probability. One thing is, it can be hard to calculate. right? Because how can you explain earlier I got a 6.5% from that 10? Yeah, that's possible. Okay, we can use the math to show that. So we got a 0, that's right, we can use the math to show that. So each sample, they have their statistic. But every time we run, they are different. They are all possible. But one thing is, we have to generate all the possible sample and calculate statistic based on each sample. So which one we will see more? We will trust more to use that to do the estimation. So that's why here we will see empirical distribution. Earlier, every time we just run one time, then we got a sample 10, the median, or sample 100, the median. But those values actually in a range. They are in a range, right? So which one I should trust more? We don't know. Then how about we do many times? So that's our empirical distribution. We based on simulated value of the statistic. We have our probability distribution, but we run many times. So that's what we call the simulation. So all the simulation, the result is our observed value. We contain all the observed value for that result. And in that proportion of time each value appear, we will make a diagram to see that. So after you make the diagram, you will see they are good approximate to the probability distribution of statistic. If the number of repetition is in the simulation is large. On the other hand, we are not only do 10 times, we are not only do 5 times, we do maybe 1,000 times or 2,000 times. After we repeat so many times in the simulation, the result from the empirical distribution will be very much closer to the population distribution. Okay, we see the example. Okay, so that's shown in the example here. Like earlier we say, we are not only do sample size 1 time or sample size 100. That's repeat to do specific sample size many times. So we need to have a function here. The function here, we define sample median. According to the size you specify, we give you the median value for the delay for that sample size. So then we just see, for example, if we do sample size 10 one time, okay, so then we got 13. But no matter how many times, yeah, that's is manually doing that. So we don't do manually, we do exactly on the size we specify here. So here, that's do 2,000 times. So in this 2,000 times, we will show the sample size 10 2,000 times. So that's have an array to keep those numbers. So we have sample, median, and array, empty array. So then we write a for loop. Okay, so then every time we do size 10 to find the median. So then we do 2,000 times. Okay, so after 2,000 times, yeah, you need to see from the diagram. So that we will see here, actually, remember our population median is 2. Okay, so earlier even we have big range, but at least the higher number located here. So that we have sample size 10, we do 2,000 times. Of course, according to the sample size 10, how about we do 100 as well? So that's why here, that's right. So we do the empirical distribution according to different size number. So we do 10, 100, and 1,000. Each one we do 2,000 times. So then, of course, they have their own array. So each one we do 2,000 times. So after we save the result, we have 3 arrays. We make a table. So this table contains sample size 10, 100, 1,000. Each one we perform 2,000 times. Now we see the histogram. Yeah, you see we have different color, right? So you can see in the size 10, yeah, they have bigger range. So that's we say the range is bigger. So size 100 is smaller. Okay, then you see size 1000 even smaller, and their highest one, the all highest one is close to our population median, about size 1000. They have mostly they are located to. So from here you can see the sample size is larger actually help, but even the sample size is smaller. When we do a lot of time, the empirical distribution result is really close to the population result.